Welcome to the 2016 NASA Ames Summer Series. To achieve human space exploration envisioned by science fiction authors, we must take into consideration life support requirements. When searching for habitable planets, we look for liquid water. Water is key to life as we know it and for human space exploration. Today's presentation, entitled Synthetic Biological Membrane, will be given by Mr. Michael Flynn. He is the principal investigator and lead for the Water Technology Development Laboratory here at NASA Ames Research Center and has over 27 years of experience. He earned a Bachelor's of Science at San Francisco State University in Mechanical Engineering. He has received numerous awards. A few of are 2 R&D 100 awards, a Wright Brothers Medal, an Arch T. Caldwell Merit Award, and 6 NASA Spotlight Awards. Please join me in welcoming Michael Flynn.
Well, thank you for coming today. I'm going to give a presentation today that deals with an area of research called life support, and it's really going to primarily focus on sort of advanced research areas in life support and sort of a new direction for enabling human exploration of space. So the objective of this primarily is to kind of put ideas into your heads, ideas that you as individual researchers here at NASA might later on write proposals and do research and funding to enable those future missions to occur. So the first question is, what is life support? All right, so life support basically is a field of research that addresses all aspects of keeping human beings alive in space. The easy part of spaceflight is getting to space. You get a big aluminum can, you buy as much explosives as you can, you get a match, you light the match, and boom, you're in outer space. But now you got to do something there. And if it's a human-tended mission, that can be very complicated because you need to keep the human being alive. All those systems that we take for granted on the Earth, the ecosystems, the biospheres that support us on Earth, don't exist in that aluminum can. So those functions need to be turned into devices, into machines, into small boxes, loaded into the spacecraft, and then operate to keep you alive in space. So the main objective of life support program is to keep the astronaut alive. It's always extremely embarrassing when the astronaut gets killed, so we don't want to have any of that happening. We want to provide an environment that is entirely safe for spaceflight applications. And that sounds like a trivial task, but that actually is the most important task of the life support system, is it has to be robust and it cannot fail in a manner that allows human life to be taken as part of the mission. The other part of it is to provide a habitable environment. Spaceflight's extremely expensive. To keep an astronaut in space costs a huge amount of money per hour, and so providing an environment where they can be very, very productive is key. Astronauts work on average 12, 16 hours a day. We try to get maximum work out of them because of the expense associated with having them in space. So it's not enough to have like a camping environment. It has to be a high-quality environment. The life support system has to operate flawlessly behind the scenes. We want to minimize the amount of maintenance associated with it. And then the final and the most important part deals with cost. We have the ability to send humans to Mars right now. We have the ability to colonize Mars right now. The technology does exist. The problem is the price is too high. NASA has done several missions where we've costed out the entire process of going to Mars, and they average around $400 billion. And Congress has told us that that is too much. We are not going to give you $400 billion to do this mission. You need to be under $100 billion and preferably around $500 million. So one of the objectives of life support is to reduce the cost of keeping human beings alive. If you can imagine, if you have to bring water and air with you, that's an extremely expensive proposition. So the ability to recycle things in situ has a dramatic impact on the cost of conducting these missions. I'm sorry, I went the wrong way. So we know a lot about life support. We know a lot about keeping human beings alive. And the reason we know so much about it is because we've been doing it. We've been doing it since, well, at least 2009, and we've been doing it on the International Space Station. The International Space Station is probably the most sustainable habitat ever developed by mankind. If you subtract out all the environmental catastrophe associated with launching it, On the International Space Station, we recycle all the water. So if you want to be an astronaut, you better be prepared to drink your own urine, because that's the only water that's available on the International Space Station. In fact, you better be prepared to drink the person sitting next to you's urine, because that's the only water. We also recycle the humidity condensate, the breath, the water in your breath that comes out. Here on Earth, we talk about carbon sequestration and global warming. Well, we do full carbon sequestration on the International Space Station. We remove all the carbon dioxide out of the atmosphere. We control around 400 ppm. That carbon is turned into methane, a fuel. We also have research looking at turning into graphitic carbon, and we're starting work looking at turning into bioplastics so we can make things like spare parts and things like that from the carbon dioxide in the atmosphere. The oxygen you breathe, that's come by, you guess it, that's also coming from your urine as well, so we want to keep that urine theme going. We purify the urine, we turn it into water, and then we put it into an oxygen generation system where we split the oxygen into hydrogen and oxygen, and the oxygen is what you breathe, right? So the International Space Station is like if you took a bunch of engineers and you locked them in a room and told them, we want the most sustainable system you can possibly develop, and money is no object. You can spend as much money on it as you possibly want. You'd end up with something like the International Space Station, completely solar powered. It's been operating since about 2009, so we have the benefit of having learned all the lessons associated with building and operating these systems. And those lessons learned are key to providing direction for future research in development of life support systems, for instance, for the colonization, exploration of Mars, going to asteroids, or going to other planets. So, life support, pretty simple. You produce outputs, wastewater, urine, humidity condensate, feces, water. You produce carbon dioxide, you produce volatile organics, you all smell, you produce volatile organics, solid waste and garbage and feces, and heat. And the objective of the life support is to take all of those outputs and make them into the inputs, right? So you can think of it as a space suit, a space station on the Earth, but the idea is that you have to close all the loops and you have to balance the entire system from the standpoint of mass. So the only thing you have to put in is energy in order to keep something alive indefinitely. And when you look at that, the biggest potential, so this is a pie chart that shows if you didn't do any recycling at all, you just brought everything with you on a mission to Mars, what would be the relative mass? And as you can see, water is the huge piece of the pie. Everything else is a much smaller piece of the pie. Most of the missions that we've done in the past, the one I was referring to that was $400 billion, assumed an open loop case, assumed that you brought all of your waste, brought all your water with you, and then turned everything into waste. So they're very expensive from the standpoint of bringing these materials along with you. So this is the area that I primarily work in, which is water, because that's the big aspect of it, the big part of it. On the International Space Station, we have a very complicated system. I kind of went through it a little bit. I'll go through it again with this diagram. But basically, you have the crew. They're the center of the whole system. The crew are producing water in urine, and they're producing water in their breath that goes into the cabin atmosphere. And then they're also producing feces. Right now, we don't do anything with the feces, but we are working on projects for recycling feces as well. The humidity goes through a condensing heat exchanger where the water is removed, and then the carbon dioxide is passed to a CO2 removal system where the carbon dioxide is removed out of it. The urine is sent to a urine recovery system where it's purified, and then that purified water is combined with the condensate water into another piece of equipment that just makes it into drinking water, make sure it's pure, make sure it's sterile water. Some of that water goes back to our oxygen generation system where the hydrogen and the oxygen is split. The oxygen is provided back to the crew. The hydrogen then is provided to the CO2 reduction system and is used to reduce the CO2 into things like methane, graphitic carbon, or bioplastics if you want to go that far to do that. So like I said, we have a lot of experience. We've been operating the ISS water recycling system since 2009. Here's a picture of the rack. It's a double rack. You're looking at about $500 million worth of equipment right there on that system. Very, very expensive piece of equipment. And the reason for that is that, well, this picture's not actually quite right. The reason for that is it's in microgravity, right? So that means that no technologies that we use on the ground actually work for this application. Almost every technology that's utilized in this system was custom designed for microgravity. So for instance, there are really no commercial pumps that work in microgravity, with the exception maybe of peristaltic pumps. Sensors, connectivity sensors, things like that, they don't work in microgravity either. Almost all of the content of this piece of equipment had to be developed through research programs, flight tested for microgravity application, and then implemented. And it's something you guys all can relate to, right? I mean, if I took a toilet, bolted it to the ceiling in this room, and then told you that's the bathroom, you got to use that toilet, you'd realize the problems associated with microgravity function. Water doesn't flow downhill. All of the assumptions that we use in water recycling systems here terrestrially really don't apply when you start doing microgravity experiments with them. The other thing is that the International Space Station's turned into this huge, complicated machine. It's definitely the most complicated device that humankind has ever made. And of that system, the most complicated components are the life support system. Not only the most complicated, but also the most dangerous components are the life support system. For instance, I talked about the water electrolyzer that makes oxygen. It takes water, it splits it into hydrogen and oxygen. When you have hydrogen and oxygen together, you have what's called a bomb, right? And so that system's extremely dangerous, and it's enclosed in a Hastelloy explosion-proof container, so that if it was to explode, it couldn't take out the entire space station. The urine, we don't want the urine to go bad. We don't want bacteria to grow into it and decompose, so we add a compound called chromic acid to it. Chromic acid is a strong carcinogen. It's also extremely corrosive, and it turns that urine into the most hazardous fluid on the International Space Station. There's no other fluid that even comes close to as hazardous as that. And then we purify it and let the astronauts drink it. So it's kind of a crazy way of doing it. So one of the key things that we've learned from building the International Space Station is that we have this real significant problem, which is there's only 24 hours in a day, right? So you can only do 24 hours a day worth of maintenance on the system. And so if your system gets really complex and you need, for instance, 26 hours a day in order to maintain it, you've created a significant problem. And that's where we are with the International Space Station, that the maintenance requirements associated with this incredibly complex system are becoming extremely problematic. It's becoming very difficult for us to keep up on all the maintenance requirements from them. So this is one of the key lessons learned from this system, which is that maintenance and repair of these mechanical devices, and the International Space Station is a mechanical device, has become a real significant problem for us. And if we're going to go to Mars, if we're going to go on a Mars mission, which is like a 2 to 3 year mission to Mars and back, we're not going to be able to do this kind of maintenance. On ISS, we can bring equipment down to Earth. It's in low Earth orbit. We can bring equipment down, we can repair it, and we can return it. On a Mars mission, we can't do any of that. Any spare parts have to go along with the mission as primary payload, and they really drive the price up dramatically. For these types of systems, for mechanical systems, NASA typically requires double or triple redundancy, and that means you either need to have 3 pieces of equipment or you need to have spare parts in order to replace the key failing components 3 times. Remember I talked about the price of these missions at around $400 billion? We need to drive the price down to below $100 billion. Well, an easy low-hanging fruit would be to develop systems that are so reliable that they don't need those kind of redundant systems, right? We could remove $2 to $3 billion out of that price tag by taking that kind of an approach, right? Now, we're not the only ones. The ISS program's not the only ones that have observed this. The National Research Council has also published a report on this topic, looking at the lessons learned from the International Space Station, and basically came to the same conclusion, that unless we make significant changes to the basic concept of how we do life support and how we support these missions, it's unlikely that we will ever get to where we need to get, which is a cost-effective mission to travel and colonize Mars. So let's talk about that for a second. Going to Mars. So let's say it's a 3-year mission, all right? That means that your system, your life support system, has to function for 3 years with minimum maintenance and no failures. Because if the life support system fails on that mission, you lose the mission. Astronauts die on the mission is lost, right? So it's a critical function of the spacecraft is to have that function. Now, what we use right now are machines. The International Space Station is composed of a lot of different machines with pumps and rotating devices that all function. And you all have an appreciation for reliability associated with machines. That's similar to the world you live in, right? I mean, you all probably have cars, or your parents have cars, and you know cars break down, right? There's no guarantee when you get in that car and you want to drive somewhere that it's going to get you to that place. And you have a AAA card, in case it breaks down, you can stay at a hotel or something like that. But what if that wasn't the case? So let me give you an example. I'm going to give you an example through a proposition. Here's my proposition. I'm going to buy everybody here a brand new car. Any kind of car you want. All right? Sounds like a pretty good deal so far, right? But in return for that, you have to do something for me. You have to drive that car. You have to drive it 24 hours a day, 7 days a week, 365 days a year for the next 3 years. That's roughly what it would take for a Mars mission, for a life support system to function on a Mars mission. You can't take it to the shop and have any maintenance done to it at all, because on a Mars mission, there's no shop to go to get maintenance done on it. And if it breaks down, I'm going to kill you. Okay? So it sounded like a good deal, but not sounding so good anymore, is it? Right? And that's the problem with mechanical devices. Mechanical devices break down. For a car to drive for 3 years continuously, you'd be putting like 500,000 miles on it. And we all know there's no way your car is going to drive for 500,000 miles without breaking down. It's just not going to happen, right? So I have another proposition, hopefully a better proposition for you. I'm still going to get your car, don't worry. You're all still going to get your car. And in return for that, you have to do something for me. And what you have to do is you have to, as a human being, just simply stay alive for 3 years, right? Just stay alive. I mean, even if you've just recently diagnosed with cancer, you could probably eke that out, 3 years, right? That's the difference between machines and biological processes, right? The level of reliability is orders of magnitude better for human beings. The average lifespan of a human being is about 65, 70 years. The average lifespan of your car running continuously is about 2 years, right? Why is this? Well, it's obvious. It's evolution, right? You as a human being, you have over 4 billion years of evolution behind you. 4 billion years of trying every different possibility and determining what is the optimal solution to longevity for your particular species that you're in. Your car has what? Generously 150 years of evolution. That's the Industrial Revolution, right? So the level of refinement that has occurred in biological processes is order of magnitude better than what exists in mechanical systems. So if we can take the lessons learned from the biological process, specifically the lessons learned from that evolutionary process, and apply it to the development of life support systems, we can achieve much higher levels of reliability. All right? So what I need is a life support system that's good for 3 years, guaranteed, will not break down, no maintenance required for it, right? Hell, if I can do 3 years, I could probably do 5 years. If I do 5 years, I could probably do 10 years. And if I can do 10 years, I could probably do 20, 30 years out of it, right? So with that proposition, the question is that at all possible? Or am I just, chasing at stars here on this? Are there any examples of water recycling systems out there that have that kind of longevity? Are there any systems, water recycling systems, that are good for 80 years, no maintenance, you never have to do anything with them, and they work perfectly for that period of time? Nobody knows of any? Threes. You are all examples of water recycling systems. So right answer. You are all examples of water recycling systems. I guess you guys are all planning on living for probably 80 years. Your small intestine takes everything you drink, all of the water, separates out any bad bacteria, viruses, any contaminants, allows the water to pass through and other things that are necessary for your body into your blood. There's no maintenance on your small intestine. There's no such thing as small intestine replacement surgery. You don't go into the shop to get it tuned up every once in a while. It just works incredibly reliably. And it works reliably because that evolutionary process has driven it that. And what it's taught us is that massively parallel systems and targeted regenerability are the key, particularly for water recycling in the small intestine system. So there are two applications that we primarily look at. One of them, of course, is the small intestine in the human body. The other one is plant root zones. There are trees in California that grow for thousands of years. They grow in dirt. I mean, what kind of water recycling system can you pour dirt into and it's not going to clog it up? I mean, there are none that we've manufactured have that capability. But plants have that capability, to have extremely long lives, live in an environment where they can't move. No matter what happens, they have to adapt to it and survive through that. And the key, of course, is the root zones, the membranes that exist inside the root zones. In the small intestine, the same thing. The key to the functionality, the key to the reliability is the membranes that exist in your small intestine. All right? Now that process, let's talk a little about the small intestine, because it's a little more than just membranes that's going on there. There's also a technique called forward osmosis. It's really extremely important to how your body works and how your small intestine works. And you guys have probably heard of forward osmosis. That's like Biology 1 class in high school. You probably learned about it, but maybe you forgot about it. So I'm just going to give you a little bit of a tutorial on what forward osmosis is. So, you drink water. That goes into your small intestine. On the other side of your small intestine is blood, right? And the water has to move from your intestine into the blood, right? The way that works is because your blood has a higher osmotic potential than what you're drinking. That's why if you're ever lost at sea in a raft, they tell you don't drink salt water, right? Because salt water has a higher osmotic potential than your blood, and so it'll cause the process to work backwards. You'll take the water out of your blood, and it'll go into your small intestine, and then you'll become even more dehydrated. So what's this osmotic potential, this magic osmotic potential, right? It's a water recycling system that doesn't need any electricity or any pumps or anything. It just kind of works, right? And I'll give you an example of it. So if I had a glass of water, I set the glass of water right here, and I filled it up with tap water. And then I took a shot glass of salt water and carefully poured the shot glass of salt water into the larger cup of fresh water, and then just left it there. Those are the kind of experiments I like, ones where you don't do anything. You just go away, have lunch, come back later. I would no longer have a ball of salt water inside the fresh water anymore, right? It would evenly mix. And I'd just have salty water inside there, right? And that's driven by a process called entropy. Entropy guides everything that occurs in the universe. Basically what it states is that it takes work to make order, and then things naturally go from order to disorder. And entropy is a measurement of the rate at which they go from order to disorder, right? So when you guys were kids and your parents would scream and yell at you and tell you to go clean up your room, and you would go clean up your room, they'd come back there a couple days later, were mad at you saying you didn't clean up your room. You were right, they were wrong. You cannot keep a room clean. It is actually impossible to keep a room clean. You can't do it, all right? So let's go back to my glass example. Now if I take my cup and I separate it in two halves, I put a membrane separating the cup into two halves. On one side I put fresh water, on the other side I put salt water, and the membrane's a special membrane. The membrane will allow water to pass, but it will not allow salts or anything else to pass across it. It's basically your small intestine. If I took your small intestine and glued it into a cup, put water on one side, salt water on the other side, set it there, left it there, went to lunch, came back 2 hours later, what would happen? So entropy's real, right? Can't change it. Something has to happen here. Water, all the fresh water will go from the freshwater side of the cup over to the saltwater side of the cup. That's what's shown in this diagram. So we start off with tap water and salt water, equal heights, membranes separating between the two of them. Let it sit for a while. Virtually all the fresh water is going to go and dilute out the salt water. Salt water is going to raise in height higher than equal to the amount of water that passes across it. And that's actually a way of measuring entropy. It's a very simple experiment to measure entropy. And I joke about small intestines, but some of the earliest entropy tables, and any of you who are engineers have worked with entropy tables before, were actually generated that way because it's an easy experiment to do. All you need is a ruler to measure the change in entropy. And they did, in fact, use small intestines, calf intestines, and things like that to run that experiment. So a very well-known experiment. The other important part of this forward osmosis concept is this membrane, this little black line. It looks pretty simple when it's a little black line, but it actually turns out it's a lot more complicated than that. In your body, your small intestine is made out of lipids. As a matter of fact, you're made out of lipids. Your skin is lipids. All the membranes in your cells are lipids. Your small intestine is lipids. Lipids are a naturally produced molecule that's produced by mammalian cells and other types of bacteria. A lipid has two tails. It has a head group, hydrophilic head group. That means that the head group likes to be in water. And it has a hydrophobic tail group, which means the tail group does not like to be in water. A cousin of the lipid is the fatty acid. Fatty acid only has one tail group. It doesn't have two tail groups, but it does have a head as well. And it has a similar hydrophobic, hydrophilic characteristics. These characteristics mean that if you look at this picture on the bottom here, if I take a bunch of these molecules and put them into a cup of water, the head groups are going to face out, and the tail groups are going to face together because the tail groups don't want to be in contact with water, which means it's going to naturally form a lipid bilayer, right? And you're made of lipid bilayers. Your skin is a lipid bilayer. Your small intestine is a lipid bilayer. The paint you put on your house is a lipid bilayer. Lipid bilayers are ubiquitous around you in products you buy and in everything. And you've all seen it. You take a little bit of soap. Soap's made of lipids. Take a little soap, put it on a glass of water, and you'll see it spread out across the top of the glass of water. It's making a lipid bilayer on it. One of the great things about these, and very important for your small intestine, is that if you rip that lipid bilayer open, it's just going to reseal itself. It's going to grow. It's going to regenerate itself. In your body, in your small intestines, there's mammalian cells that are on the back side of the small intestine that hyperexpress lipids. So the membrane itself is soaking in lipids and fatty acids as well. Fatty acids turn out to be extremely important as well. So your small intestine is a regenerative membrane. It's a membrane that when it gets damaged, it can repair itself. The fatty acids provide some protection to it. So it means when you eat something, consume something, if it forms a solid that's going to stick to the membrane, it's going to stick to the fatty acid coating before it's going to stick to the membrane, and the fatty acids will just wash off as part of the bacteria. So that's what we want to develop, right? We want to develop a water recycling system that simulates the small intestine, and that's the key aspect of the small intestine that provides its longevity, its 80 plus, 90-year life associated with it. So here's a pictorial that kind of shows how this process would work. So down here we have a solution. In this solution, we've taken E. coli and we've genetically engineered the E. coli so that the E. coli are hyper-expressing fatty acids, and these are the fatty acids, and also lipids as well. We use E. coli rather than mammalian cells because mammalian cells are very hard to grow, and E. coli is almost impossible to kill. So it makes it a lot easier. So the lipids then can replace any damage that occurs. This is the lipid bilayer here. So this would be the actual membrane itself. And if there's any damage to this lipid membrane, the lipids in solution can replace the missing lipids in there. But more importantly than that are the fatty acids. The fatty acids are permeable through this lipid bilayer membrane. And so when they're on this side, we modify this solution so we have a high solubility of fatty acids. When they permeate through the membrane into the feed solution, they have a very low solubility. So they form a solid phase on the surface of the membrane. This is like a biologically sacrificial coating on the surface of the membranes. So if, for instance, if radiation in space attacks the water, produces hydroxyl radicals that would oxidize the membrane, damage the membrane, they're going to damage the fatty acid layer before they damage the lipid layer. If anything is going to precipitate out, shown here, they're going to attach themselves to the actual fatty acid layer rather than the lipid layer, and then the flow of fluid across the top strips off the fatty acids. When the fatty acids are stripped off, then more fatty acids permeate through the membrane to replace those. So that's the basis of the concept of this regenerable membrane. It pretty much follows the way your small intestine works. At least it follows sort of the lessons learned of how your small intestine works. It's not exactly the same as your small intestine, but the idea is that it mimics that regenerable capability. It's taking the lessons learned from that evolutionary development of your small intestine and applying it to a mechanical system. So just kind of a summary, we actually have a water recycling process that we utilize that in, and that's this system right here. So the way this works, this osmotic agent loop is where the bacteria grow. So the genetically engineered bacteria are in this loop. The feed, which is urine and humidity condensate, is on the other side. And this is the biomembrane right here. The red would be the biomembrane. So the fatty acids are applied to this side of the membrane, and then the genetically engineered bacteria on the other side. So this solution is very high in concentration in lipids and fatty acids, and the lipids and fatty acids permeate across the membrane in here and provide a protective coating to it. All right, so that's the synthetic biological membrane technology. Now there are other lessons that we've learned from the International Space Station that also have taken us in this direction of using the experience of evolution to resolve our problems. And I'm going to talk about two of those here for the rest of the presentation. One of them deals with when you have a closed spacecraft environment, things build up in that environment. Trace contaminants that you didn't even know existed in that environment over very long periods of time. If they don't have a method of being removed, they're going to build up in the spacecraft cabin. And we're going to talk about some of those applications. And then the other one deals with this issue of things precipitating out and the problems associated with astronaut bone loss and how the impact that has on water recycling systems. Okay, so one of the projects that we're working on is dealing with the International Space Station, a failure of the International Space Station water recycling system to be able to remove a particular trace contaminant that's building up in the space environment. It actually exists in the air environment. That's where it's coming from. It's coming in through the condensing heat exchanger and getting into the water treatment system. And this is a plot showing from 2010 all the way to 2016. looking at total organic carbon content of the output of what's called a multi-filtration bed. And as you can see, normally we have very low concentration of organics, but then every once in a while we have these events that are occurring that are causing contaminants to appear in high concentrations and occasionally exceed our minimal acceptable level for the product water quality. And what's happening here is that we have this compound, it's in a very, very low concentration. But one of the technologies in the ISS system is an absorption bed. And it builds up these compounds on it, and then eventually it desorbs those compounds. And that's why we see these peaks coming out. And so what we want to do is we want to get a technology that will allow us to remove these compounds out of there. So this is a flow diagram of the ISS system. I remember I was referring to these multi-filtration beds. So water comes in here, goes through a filter, goes through this multi-filtration bed, then it goes through this catalytic reactor that oxidizes it. And the problem is this multi-filtration bed is failing over long periods of time. So the approach is to replace those multi-filtration beds with a biomembrane, with a biological membrane to fix that. And we're using a technique, a membrane called an Aquaporin membrane. It's very similar to the membrane I just described to you. It's a lipid-based membrane, but it has a protein embedded in it called an aquaporin protein. And you guys are all based on aquaporin proteins. Aquaporin proteins are how your kidneys work in separating water from your blood. They're key in your cellular function for increased flux water channels in cells. They're commonly found in root zones of plants as well to accelerate water transport across membranes. It's a very unique protein because it's charged in the center, it has a positive charge in the center. So that means that any sort of salts or charged molecules that pass through that, you'd have to get both charges to go through. You'd have to get the positive and the negative to go through. And you can't get the positive to go through because the center of the protein has a positive charge associated with it. So water can pass through it, salts can't pass through it. Any organics, any organic acids or any organics that have a charge can't pass through it, even if they're small enough to pass through the pore in the system. The Nobel Prize was actually awarded to the person who found this in 2013, and there have been several development activities that have come out of that experience, and one of them is developing membranes based with these aquaporin proteins into it. So we've been working with these proteins for some time now. This actually shows what the membranes actually look like. They're little fibers that have been coated with lipids and the aquaporin proteins and these little contactors. We've been doing experiments on the International Space Station where we've been taking wastewater on the space station and processing through them. And we've also been doing a lot of ground-based work simulating the wastewater that's on the International Space Station and processing it through. Just some typical results. These are mainly contaminants out of the cabin, right? So they're semi-volatile organics. Normally, membranes cannot reject semi-volatile contaminants. It's only with these aquaporin proteins that we can get any rejection of semi-volatile contaminants out of these membranes. As you can see, we have about a 50% reduction in the total organic carbon of the water going through it, which meets our target for the downstream volatile removal assembly. And this is the problematic compound, DMSD, that's building up in the International Space Station, and we can really dramatically have an impact on that. It actually rejects DMSD very well. From about 20 parts per million, we can get it down to around 1 or 2 parts per million and hold it there pretty reliably. All right? So that's another example of basically a biological technology, a biological technology that's been optimized. That protein, the structure of that protein has been optimized over the 4 billion years of life that has existed here on Earth. And it is an endpoint that is perfectly designed for doing separations of biological fluids. And of course, on the space station, our wastewater is a biological fluid. So, and that project is actually moving to a flight project. And so next year it'll be transferring to a flight project. And then the year after that, they'll be working to replace the multi-filtration beds on ISS with that technology. Now, another technology that I want to talk about that isn't actually biological, but I need to sort of set the stage for another biological technology, deals with a failure that we had on the International Space Station almost a month after we installed the water recycling system on the ISS. The urine processing system actually stopped functioning. And it stopped functioning because there was a compound that was precipitating out in it called calcium sulfate. Calcium sulfate comes from the fact that when you take astronauts and you put them in space, they lose bone mass. Since they don't have the loading that you typically have here on Earth, they're floating around in space, your body automatically redistributes calcium in your body. It moves bone from your legs and moves it up to your head and changes it around. And also, you excrete an awful lot more calcium in your urine under those circumstances. And NASA is a very conservative organization, so we all freak out about that. And we give them lots of calcium supplements and things like that that do virtually nothing because it's a regulatory process. And so all that calcium ends up in the urine. And if it mixes with sulfate or carbon dioxide, it produces calcium sulfate, calcium carbonate as a byproduct. And that was a failure mode for the ISS water recycling system. So we had to bring that thing back down to Earth, get a chisel, chip out all the calcium out of it, and then refly it back up to the International Space Station. It cost about $100 million to do that. Very, very expensive. So needless to say, NASA was very interested in developing technologies that would prevent that from happening. And so we had a lot of funding to look at different technologies. And this is one of the technologies called electrodialysis metathesis that allows us to actually deal with this calcium issue and remove it from solution and prevent it from causing problems. We integrated it with the space station urine processor. That's basically what's on the right-hand side there. And what we did is we turned the system on, and then we ran the urine processor at very high water recovery rates, and then we just tried to make it fail, tried to see if we could make it fail. These are some pictures that show the inside of that system. These discs here are the heat transfer surface, and you can see here is with the electrodialysis metathesis system off, and you can see the calcium scale formation. And then these are a bunch of different runs where we had the system on. As you can see, it totally resolves that calcium problem. So the basic approach was NASA had this problem. Problem was that these endpoints, these byproducts of treating human waste are precipitating out of solution. They're causing problems. They're causing systems to fail and making them have to come back to Earth, be repaired, and come up with solutions to solve that problem. Not a good situation if you're on your way to Mars to have those kinds of failure modes be apparent. A much better approach is to sort of change your entire philosophy as to how you would conduct one of these systems. So this is back another picture of this bone. This is astronaut bone, basically is what it is. There's two different kinds. There's the green kind, that's Russian astronaut bone. And there's the brown kind, that's US astronaut bone there. It's kind of complicated why the colors are different. But basically what this material is it's gypsum. So mixtures of calcium sulfate and calcium carbonate are commonly called gypsum. Another word you've probably heard of is wallboard. So sheetrock that's used in houses. Probably in this room we have sheetrock here, right? So on ISS we have developed a system where if this material fails, it causes the water recycling system to fail. However, it's a useful product. I mean, it's a construction material. So we're kind of taking the wrong approach here. Rather than having this endpoint be a failure mode, we should have this endpoint be something of value. If you're on your way to Mars, the waste that you have is the best resource that you have, the best material that you have. So the more you can utilize that waste for some beneficial purpose, the better off you're going to be. So this is a project that was called Water Walls. It was funded through the NIAC proposal, and that was the objective of this. It was to take all of those human waste byproducts, all of the nastiest, most disgusting byproducts, the concentrated urine byproduct, the concentrated feces, all the garbage that's produced on the space station, all this bone, astronaut bone material that's been produced, and turn it into something that's useful for that space mission. So the idea was you have an inflatable habitat. This is a Bigelow inflatable habitat. And then you basically start off with some water in some bags on the walls. And as time goes on, the astronauts produce waste, and the waste that the astronauts produce is used to convert the inflatable structure into a rigid structure. So this is like a living organism. It has a birth, it's launched. Inflatable structure is launched, the inflatable structure is deployed. Then this habitat has a life, and the life is during the period of time that you have astronauts in it, and they're producing waste, and those wastes then are filling out the construction of the entire habitat. And then it has a death, and the death, of course, is when it's all used up. All the capacity of the system is used up, and it just simply becomes an enclosed volume in orbit between Earth and Mars, like a taxi system for going between the Earth and the Mars. Now, the real objective with this waste is radiation. Like I said before, we have the technology to go to Mars. The problem is we can't afford to go to Mars. And the real reason we can't afford to go to Mars is radiation protection. You're going to get a good dose of radiation on your way to Mars. You're going to get galactic radiation, and you're going to get solar radiation. If there's a sun flare occurs on your way to Mars, you could just get killed by the radiation. Radiation levels could be high enough that it would just kill you on the spot. The galactic radiation is just going to cause a significant problem for you no matter what. It's more of a constant. This is a plot that shows galactic galactic radiation and solar radiation, not taking into account sun flares on solar radiation, and the maximum dose limit that a human being can get of radiation during the period of time. And as you can see, we can get right up to around like 170 days. And after 170 days, you are definitely giving yourself cancer on this mission, right? So that's a big problem. So NASA has to provide radiation protection material. This is assuming an aluminum canister like an International Space Station canister. So we need to provide radiation protection. That means we need to bring material from the ground in order to provide radiation protection. If you look at that for a 240-day space mission, you're talking about 130,000 kilograms of water that would be required to provide radiation protection. Turns out the only things that really work for radiation protection are water and polyethylene. It's really the hydrogen is the key. You need to get hydrogen. Hydrogen is the key for providing radiation protection. And 130,000 kilograms of water means this mission is not going to happen. There's no way we can afford to launch those kinds of volumes into space. If you just look at solar radiation, it's not quite as bad. You need about 25,000 kilograms of water in that application. So where are we going to get all this water? Where are we going to get all this radiation protection material? Well, we have the International Space Station. It has a water recycling system on it, and it produces a concentrated byproduct. They also produce feces on the International Space Station. They produce garbage on the International Space Station. So the water walls concept is to harvest all of that stuff, that disgusting byproducts of human waste, process it, and then use it for radiation protection in a mission, in a spacecraft that would be traveling between Earth and Mars. So how does that work? So if you look at that, at the masses that are required for that, if you look at a 6-person crew on the International Space Station achieving 80% water recovery, they're going to produce about 6,500 kilograms a year, which means for solar radiation, it would only take about 4 years to stockpile enough material to provide that radiation protection material for a Bigelow type inflatable structure application. And if you want to do galactic radiation, it would take about 10 years to produce that kind of wastewater. You don't have to launch anything from the ground. You're basically getting all of this material in orbit for free. As a matter of fact, we typically destroy all that waste by re-entry into Earth's atmosphere, which costs money too, so you'll actually save money. So the basic concept, and this is there's a bunch of different life support functions that all fall into the same concept, and I have these pictorial graphics to kind of describe how this works, is you have the crew in the spacecraft. All of their wastewater is put into these small little bags. The bags then process the wastewater using forward osmosis to remove the water out of them, and the water then goes through an RO system and is provided back to the crew. The bags eventually become completely filled with this basically gross, solid materials. It's still mostly water, but it has a lot of solids, byproducts into it. And then those are vacuum processed, and then the solid bags become like tiles. They become radiation protection tiles. And then these tiles are placed on the outside wall of the spacecraft. And so as a function of time, the spacecraft capacity for radiation protection increases as the humans generate more and more waste. The basic bag we use is commercially available product. It's a Hydration Technologies X-Pack bag. It's a forward osmosis bag. This is a great little product, particularly if you live here in California where there's earthquakes, right? If earthquakes, they tell you should keep 5 gallons of water underneath your bed. And every year you should replace the 5 gallons of water, right? How many people do that? Nobody does that, right? Well, with this little bag, you can buy this little bag. It has about a 10-year life. You just throw that under your bed, and when there's an earthquake and you need water, wake up, pee in the bag, and you got all the water you want. As a matter of fact, we actually sometimes have cocktail hours where we make all the interns pee in a bag, and then we have a cocktail hour and make them all drink their own urine. They get really excited about that. This is an example of an actual test producing this material. So this is urine, brine concentrates, feces, and garbage all mixed together. And then we process it in the bag, and you can kind of see we produce this kind of tarry material. It's kind of like toffee, basically, is what it is. And we took those samples and sent them and had radiation dosing done with them. What we found was that we actually can dry them a little too much. And we need to dry them a little less. They need to have a little higher water content. Our real focus was dry them enough so that bacteria can't grow in them. So they're basically sterile, so nothing can grow inside of them. But that actually resulted in a little bit too low water content. So we need some more processing to do there. But that's the basic idea. So you're going to take these bags, all those endpoints of the life support system are going to be processed inside the bags. You won't cut them open. And the bags are assembled either on the outside or the inside of the spacecraft to provide radiation protection as a function of time, right? So the system has a life expectancy. We also do this with, for humidity control. Same thing, we have a bag. The bag has a different type of membrane that allows gases to pass through it. So the humidity, the water vapor in the air goes inside the bag. The water is cooled through a cooling system, and then it accumulates the water in the bag. We recycle the water in the bag and provide fresh water back to the crew. Carbon dioxide control and oxygen generation is done by growing algae inside these bags. We populate them with algae. Again, it's a membrane that allows gas to pass through it. The carbon dioxide goes into the bag. The algae use the carbon dioxide as a food source. They also electrolyze water and produce oxygen, so oxygen comes out of it. And then eventually the bag becomes completely full of dead algae, and then it's processed similar to the wastewater and turned into a tile used for radiation protection as well. Now these systems are put on the outside, so these are the bags here on the outside of the habitat, the Bigelow habitat, and that's kind of a cross-section showing it takes multiple layers of bag. One bag is not going to provide enough radiation protection, so you have to provide multiple layers of the bags in order to get the targeted level of radiation protection. This is a diagram that just kind of goes into a little bit more detail on how these bags would be placed and how they would be plumbed together on the inside. There's a protective screen so that you don't put a hole in them if something gets free out of the system. So this is an analysis that we did looking at the radiation protection. So these are layers of bags. How many layers of bags would you need in order to get this protection level? So this is for the solar radiation, and this is for the galactic radiation. And really, within about 2 layers of bags, we can pretty much sequester all of these solar radiation very simply. The galactic radiation is a much more difficult one to deal with. It takes actually quite a few layers of bags in order to get to an acceptable level of radiation exposure. Now, what you have to do is you have to tailor the number of bags and number of radiation protection for the duration of the mission, because of course radiation is an exposure function, and so it's a function of how often it is exposed. The other thing you get for this technology is you get all of your life support functions integrated into them. This is a very complicated diagram. I'm not going to go through it in a lot of detail, but very similar to that one I showed for the International Space Station system earlier in the presentation, where the crew is the center. We have an air revitalization system that has the algae in it and humidity control. We also have bags used for volatile contaminant destruction, climate control, and then the urine and black water processing, and there are also some power systems that we can integrate into that as well for doing it. How much time do I have left? 5, perfect. So what I've outlined here are these basic concepts of taking these biological functions, not actually biology, but the biological functions, and integrating them into mechanical systems to produce a new class of technologies that are integrated, what we call biologic organs or biologic functions. We haven't only been doing those for spaceflight applications, we've also been doing terrestrial applications for that. And this is a picture of the green building. It's right across the street from us, right over here. And that system has a water recycling system. It has a forward osmosis water recycling system integrated into it, so it functions the same basic way your small intestine functions. It takes all the hygiene water, purifies it, and we use it for flushing toilets in the building, and that's a picture of the system. It's been operating now for about 2 years, pretty much continuously. We actually haven't been putting water back in the building yet. That's something that's going to happen pretty soon. NASA, we're really interested in testing it and getting operational data out of it. That's the primary objective. It's a way for us to test forward osmosis systems for spaceflight applications for years and years and years with human waste as the input into them. The other thing that came out of that process, so the Army heard about the green building application, and they asked us to build one of these biologic systems for them. So we built a forward operating base water recycling system. It uses the synthetic biological membrane inside of it. And this is for forward operating base. Forward operating base is the sort of the smallest fixed facility that the Army operates out in the field. And if you look at conflicts like Iraq and Afghanistan, the highest death rate associated with those was contract employees, so local Afghani, Iraqi employees working for the U.S. Army, trucking material to forward operating bases, trucking water, fuel to forward operating bases, and then waste back out from forward operating bases. So the Army wants to develop a forward operating base that's completely self-sufficient, similar to like a Mars-based kind of an application. And so this technology was developed for that. It's been very successful. It's gone through a very competitive process, and it does look like it is going to become the baseline system for the U.S. Army in the future. Okay, so the conclusions here. So the objective of this presentation was to give all of you guys ideas so that when you go on, do master's, PhD theses, you know what you're supposed to be doing. You write a proposal, you submit it to NASA, I review your proposal, and you get funding. right? It's a pretty simple equation. And what we're really interested in is reliability issues. Any kind of issues that address reliability, that's a key aspect in the life support arena. The area that we're doing primarily work in is looking at integrating biological and mechanical systems together, not developing biological systems. We have done that before. We've done bioreactors to treat wastewater. Bioreactors produce carbon dioxide. Things that produce carbon dioxide, we call them crew members. We don't need any more crew members. We don't want any more carbon dioxide in the atmosphere. But integrating biological systems into making, for instance, biological materials that have unique characteristics associated with them that provide reliability, those are the types of things that we're looking for. So some examples of other projects that we've been looking at is there's a university group that's actually making CCD cameras out of biological. So they grow bacteria, they genetically engineer the bacteria to express a protein. When light hits the bacteria, that protein is expressed, the protein's conductive, and you can measure the change in the amount of proteins into it. And you can actually make a small camera that works using that technique. And CCD cameras are very susceptible to radiation, so they're a problem. Heart, think of your heart. Your heart is a pump. Runs 24 hours a day, 7 days a week, 365 days a year for 80 years. I mean, there are no pumps commercially or NASA that come anywhere near that level of reliability. That is the most reliable pump by far out there. We also have a project where we're looking at developing an autoimmune system, a synthetic immune system. So the idea is you're on your way to Mars and you get diagnosed with some sort of a disease or some sort of sickness. And this system allows you to, like your body would, to produce antibiotics, to produce proteins, to produce enzymes, to respond to the disease that you have there. And that's, again, done by genetically engineering E. coli to express those compounds. So, all right, so that's all time I have for. So if anybody has any questions, thank you.
Let's take only 2 questions. So we have time for a couple of questions. So if you have a question, raise your hand, wait for the microphone, and please ask. 1 question only. Thank you.
You want to stand up? Just stand up.
Great talk, Michael. I have a specific question for you and then something general to follow. The specific question is that biological systems are wonderful, no doubt, but it's kind of a misconception to say that they're so stable because they're repairing themselves all the time. And the repair takes energy. So that the system, although it's wonderfully efficient in terms of how long it lasts, it's actually repaired a lot. Yeah. So you kind of described that with the lipids.
Yeah, so let me give you an example of that. So in the biomembrane project, where we were repairing the membrane as it gets damaged, we need a source of energy, right, to do that. And there's 2 sources of energy that we're looking at. One of them is the feed. The feed is human waste. So that has nitrogen, phosphorus, sulfur in it, has an organic content. And so the idea is the bacteria would actually live off of that organic content that's there. Somewhat problematic because it is waste, so a lot of the energy has been removed out of it. It's not a high energy solution. So another approach we're looking at is using actually cyanobacteria, genetically engineering cyanobacteria to express the fatty acids that we're interested in. And then we could use carbon dioxide and crew cabin light as a source of energy. But you're absolutely correct. Biological systems do carry some overhead. I think that's what you're kind of driving at, associated with their operating. But in many cases, like with regard to a separation membrane is treating human waste, I mean, bacteria is going to grow in there one way or another. So you might as well have it do something good for you, right?
Water scarcity is definitely an issue in space, but as you highlighted with the Army topic, that it's also an issue on Earth. There are a lot of people who don't have access to clean water. Are there any lessons from your studies so far in forward osmosis membranes that could be applied to water technologies here on Earth? Yeah,
so this is an area that we do actually a lot of work into, and I only kind of touched on that with the Army system. So here in California, we have a drought, right? And the governor comes out and says, you got to cut your water consumption by 20%, right? Why can't I just pull out my credit card and solve that problem? Why can't I go down to Home Depot with my credit card and just eliminate the drought as a problem? Go down there, buy a water recycling system, hook it up in my house, right? Well, the reason is because you go down there, you buy that, put it in your house, you're never going to maintain it, right? You're never going to test it. You're never going to make sure the water is good that's coming out of it. You're just going to go there, plug it in, and that thing better work without any maintenance for a predetermined life period of time, and it better be cheap to operate, right? It's almost identical to the criteria for a Mars mission. That system needs to run continuously for a 3-year period of time with no maintenance and not require any testing, because you're on your way to Mars. If the tests say that you can't drink the water, that's not particularly useful because you're drinking the water anyway, right? I mean, you don't have any option, any backup situation. So to take put the power in the consumer's hands to address the water recycling issue, you need to have water recycling systems that are very, very reliable, that don't fail. And so the biomembrane project is a project that we feel is a real game changer in that area, because that allows you then to develop a water recycling system, for instance, that you might hook up to your washing machine that would recycle the water in your washing machine. And it has self-repair characteristics to it, right? So fine, don't maintain it. Don't pay any attention to it. That thing will just sit over there and repair itself on its own. Right, so you're absolutely correct. And we have some big proposals in the state of California to do human health studies and human factor studies and do 300, 400 homes, put water recycling systems into them that are going right now through the state. And whether they get funded or not depends on the state, I guess. Yeah.
So with that, please join me in thanking Michael Flynn for an excellent talk. Thank you very much.